All right, so we're going to pick back up and take a look at another one that is a series of numbers where we're adding them together. So one of our problem-solving strategies is to examine a related problem. So clearly this problem relates to Gauss's problem, right? I mean, it's not starting from 1 and going to 100, but it's got the same sort of feel to it. So this idea of examining a related problem means exactly what happens when you guys take a math book and you look back in the math book for a problem that's kind of like the one you're supposed to be doing, and you say, okay, what approach did they do? Oh, they added this to both sides. Oh, then I need to divide by that. Oh, and then I need to make sure my answer looks like such and such. That's all that is. So you've used this approach your entire career in mathematics. So this is an example of one of those, and I wanted to show you how to do what Gauss did when the numbers aren't the same numbers Gauss had. So if you take a look, we can do the same kind of thing with these numbers. And you take a look at what they're adding up to. And of course, we could continue and we could write more numbers if we wanted to verify, make sure in our own, self-conscious that it's really broken out for us, whatever. But it will. If we take and we add 36 plus 147, what do we get?
So 183.
It is 183. Thank you very much. All right, so we have 183, and they're all going to do this as we move our way inward, a piece at a time. They all add up to 183. So we've got a whole bunch of 183. So do you remember what we did after we established, last time it was 101, they all added up to? What did we do next?
101 plus, like, we actually figured out the
Yeah, so we took like each one of our terms and we replaced it with the number that it added to, which was 101, right, Caleb? Okay. So we're going to add 183 together a whole bunch of times. At least that's how we're going to write that. But what we talked about last time is that when we did that, it wasn't exactly the same as the sum we started with. What was it actually? Twice as much. And it's exactly the same this time. This is twice as much. I've replaced every pair that adds up to 183 with 183 twice. That's twice as many as I was needed. Now, how many 183s are there? So last time there was 100. But why was there 100 of them? It was the numbers from 1 to 100. This is the numbers 1 to 100, right? So 111. And how do you get 111? Close. Okay, so we take the last number that we got, 147, and we would subtract 1 before the number that we have as our first number, right? Because we have 36, but I don't have 35. So in other words, I don't get all the numbers from 1 to 35, but I get everything after that. So this ends up being, what, 112? So there's actually 112 of these numbers. So instead of writing 183 and actually telling my calculator to do this, oops, I didn't mean that to look like a 5, it's an S. Instead of having 183 a bunch of times, we're really going to do 183 times 112. Then what? Then we would divide by 2. All right, so many of you have already told me that you don't have calculators today. I think there was something that did. So somebody with a calculator, let's multiply 183 times 112 and then divide by 2.
10,248.
Really? Caleb, the only one with calculator? Okay, we can list a couple of lists. That's good. Okay, what did you get, Caleb?
10,248.
That's what I have written down too. Excellent. All right, so does this process make sense? Now, you should be able to do this with any set of numbers, right? Sure. One caveat. Let's say, for instance, instead of these set of numbers, do you notice it all increased by 1? I went 36, 37, 38. What if it increased by 2? How would that change things? Would it change the summing ability? Would I still be able to add the first one and the last one and add the second one and the second and the last one? Yep, I'd still be able to do that. That would not change. what would change? No, you mean like this 2? Is this what you mean? Or, oh, this number. Yes, I would not have 112 of these, right? If I only had the even numbers instead, or I only had the odd numbers, how then would I find out how many I have? Yeah. So in this case, if I had this, I would have half as many. I'd only have, what, 56 in this one, right? I'd have 56 numbers. But that's the only thing that would change. The process, everything else would stay the same. They would just change that one little piece of the puzzle. Okay? All right, let's take a look at something else. So I know I've got some athletes in here. How many of you have been in leagues and playing some kind of thing before? Round robin league, like table tennis, things where you play those games. Do you ever play cards, right? Spades or something like that, and you play this person, that person, do a round robin thing. All right, so this is the kind of idea. So, so the YMCA is about to have different leagues starting for the fall, soccer and volleyball in particular. So once they get however many teams they're going to have, they need to know how they're going to schedule that. They know how many games they have to schedule, right? Well, in order to know how many games they have to schedule, they have to do a problem like this. And this is what has to really happen. So in this case, we're talking about a soccer league with 10 teams, and each team is going to play each other one time, and the question is how many games are played. There's lots of ways to do this problem. I want to show you a way to think about it using an example, or by examining a simpler case. So let's back up and let's say, instead of having 10 teams, let's say we only had 3 teams, okay? Let's call them teams A, B, C. So again, instead of having, 10, I've pared it down to something that I can work with more easily. Okay? Well, I could have teams A and B play each other. I could have teams B and C play each other. And I could have teams A and C play each other. Now, do I need to also write down BA, CB, and CA? No. They're still playing each other, right? So this is playing each other one time, and it doesn't matter who's the home team or the away team. They've still played the game, kind of an idea. All right, so I ended up with 3 teams, and they played 3 games. So is it just 10 games? Let's try 4 teams, okay? All right, so now I've got AB, I've got AC, and I've got AD, and I've got BC, and I've got BD, and I've got CD. Did I get them all? So now I have 6. So it's not just the number of teams. So I can't generalize that idea. Something else needs to be going on. Well, let's go back here for just a moment and take a look at what would happen if I wrote these down. So let's take a look at our team A. Team A, how many games does Team A play? 2 games. How many games does Team B play? 2 games. And how many games does Team C play? 2 games. So if I counted all of those separately, I would end up with 2 times 2 times 2. I would actually end up with 6. I'm sorry, it's not 6. I added them up. I ended up with 6 of them instead. And I really only have 3, right? What about down here? Well, if I do 3 games for each of them, right? How many would that be? That'd be 12, but how many games do I really have going on? 6. Well, that sort of looks like there's something going on that's pattern-like, doesn't it? This was 6, and there's actually only 3, and then I counted 12, and there's actually only 6. What's going on? It's half. And the reason it's half is because we don't count AB and BA, right? Those are actually the same game, you just don't double count it. So if we have 10 teams, how many games does each individual team play? They play 9 games. So one might think that we should do 10 times 9, right? That would be the same idea here as saying 3 times 2, or here is saying 4 times 2, right? But it is a 10 times 9. What is it? what did we do? What did we do once I got my 6 or my 12 here? I divided by 2 because it took out those double counting, right? And that's exactly what's going on here as well. I can divide this by 2 because that takes out the fact that I counted that game for team A and I counted that game for team B when I did 10 times 9. Does that make sense? So how many do I end up getting? 45. So this league needs to know this because they need to have arrangements made in the schedule somehow for 45 games between however many weeks. They've got to have umpires, they've got to pay in and all that kind of stuff, right? This is the kind of information that they need to research in order to do their league. Okay, so let's put a note on here just so in case you guys didn't actually write it down that this removes double counting. That's why we divided by 2, is because it actually gets double counted. All right. This is one of my favorite examples because it's an example that you would see used later in some algebra course. And there's great algebra ways to do the problem, but there's so much more concrete ways that you guys could do this problem with probably about a 2nd grader. Okay? Take a look. We've got a store that sells bicycles and tricycles. They have 15 cycles. So bicycles and tricycles combined. There's 15 of these, vehicles. But there are 35 wheels. And the question is, how many of each type of cycle are in the store? So, I'm going to draw a picture, and I'll warn you in advance that I am not an artist. So these are not going to look like bicycles or tricycles, okay? But it's going to be a picture nonetheless. So we're going to take a cycle, and I'm going to put at least 2 wheels on every single one of them, right? Because every cycle has at least 2 wheels. So I'm actually going to draw how many cycles? 15. And I'm going to start out automatically when I draw my cycles with all of them having 2 wheels. All right, there's 6 of them. So far, I know they look like cheeries. So far, I have 15 cycles. And how many wheels do I have? I have 30. How many wheels am I supposed to have? 35. So what do I need to do? Add 5 more. And I do it one at a time, right? Because their only option is a tricycle. So let's do this. Do I have 35? Okay. So how many bikes do I have? 10? Yeah. And how many trikes? And did you see a single variable on the board? No, it's really concrete. Yeah. You can do the same thing. I've seen other examples of problems like this with there's chickens and cats in the barnyard, right? Chickens have how many feet? 2. And cats have how many? 4. Could you draw the same kind of picture? Sure, right? These kinds of things. What you see happen later on is, of course, you use something like a system of equations to solve this in algebra, right? But you can do this kind of a problem at a much younger age if you're using diagrams. So I like diagrams. Guess and check. Did you know that guess and check is not cheating? It isn't cheating. One of the things that you want to be sure to be aware of, though, is that guess and check, random guessing and checking, is not very helpful. I have a distinct memory of being in elementary school, and we had a substitute who was trying to kill time before recess, one of those kind of things. And so she did I'm guessing it, I'm thinking of a number between 1 and 100. And we had some dumb kids in the class, and they weren't thinking. And they just randomly guessed numbers. And even as I'm sitting there thinking, and I don't know what grade it was, but I'm thinking, you're never going to guess the number. I'm like, yeah, maybe, right? But this is not a very productive way to do this. Her restriction was she would only answer yes or no questions. So So the appropriate kinds of questions to ask would be something like, is it above 50? And if the answer is no, then you rule out half the numbers, right? Right? This is like 20 questions, same kind of an idea. There are good questions to ask and there are just not so helpful questions to ask, okay? So guessing and checking. One of the things you want to make sure when you're guessing and checking you're doing is keeping a record of what you guessed. Because nothing's more annoying than the same person guessing what's already been guessed and you already know the answer is no, right? So we're going to keep a little bit careful track of that too. So I want to show you that there's actually 3 things that are going to go on in this particular problem. I'm going to use guessing and checking. I'm also going to make a diagram, and I'm going to draw a table. Woo! It's a lot to do one problem, but it shows a lot of information. So let's take a look at the question. We have 48 feet of fencing, and we wish to make an enclosure along the side of an existing barn. What length would the sides, I should not say sides, but sides, need to be to have the greatest area enclosed? All right, so here's my diagram that I mentioned. I have got a barn, and I want to draw an enclosure. You know, like I want to fence some area in. Maybe it's for the dog to run or for the chickens to have a chicken area. I don't know. But I want to fence something in. So my fence, and I think it said it's a rectangular, right? It didn't say. I don't think I'm going to make a circle fence or anything, so I think rectangular is probably the most reasonable, and it is correct too. So we're going to go with rectangular enclosure over here. Tell me something you know about the sides of that enclosure if I'd drawn it well. Yeah, the sides, the red pieces. Okay, so one of the things by being along the side of the fence that I don't need is I don't need fencing along the barn itself. Yeah, actually, if I were doing standalone fence, you're right, I would need 4 sides of side 12, and that would be the greatest area. But what do you know about this shape? What do you know about this side and this side? They're equal, right? So whatever number I put here, I'm going to put here. And this one, we don't have that stipulation. It could be anything, right? So this is where the guessing and checking part goes, all right? So we're going to keep track. This is my table, my guess. All right, so somebody give me a side length for the side of this fence. So we're going to call this, just so that I can talk about it, we'll call this one S, and this one we'll call, how about we just call it X? So we have going to have S and X, and we don't need the barrels and such to reference them as we're talking. We don't really need it for anything. But what do you want to let S be? What do you want to try? How about we try 12 that you had mentioned? Okay, so let's try a 12. So if I have side lengths 12, I would have 2 12s and what? 24. Right? And how do I know it's 24, Kayla?
Because 48 minus 12.
Yeah, you're using the fact that I have 48 feet of fence, right? They all have to add up to 48. All right, so how do I find the area then? This is the checking part. How do I find area of a rectangle? Length times width. And in this case, that's 12 times 24. 288. And the units would be in feet, because I'm feet right here. So it would be feet squared. Okay, so this is one option. That sounds pretty good. But maybe there's something that's more. So somebody else, give me another option of something I could guess. 10. So if I did 10, I'd have 2 10s. And what? 28. Alrighty, so then I would take 10 times 8.
That's 20.
Oh, oops, yeah, 28. 10 times 28, and I would get 280. Right, so the question to yourself is, which one's winning?
Longer sides.
Right now, the 12, 12, 24 is winning, right? That one's doing better. So, I need another guess. What was it? 16. Okay, so something bigger than 12, right? Okay, so let's try 16. If I do 16 and 16, what's my other one? Is it 16?
16.
The third one as well? So let's try 16 times 16 for my area. 256. So I think at this point I'm fairly confident that the answer is somewhere in between 10 and 16, right? Because 12 is between 10 and 16, and if I went higher than 12, and if I went much lower than 12 on either side, I've gotten lower numbers. So what else could I check? Because it still could be that there's a slightly different or slightly higher number. 14? And 20? So what's 14 times 20? 280. I think I've seen that number before. I need to check at least one more thing, I guess. I either need to check 13 or 11. Either one will be fine, because notice this. This one to this one was 2 less. And this one to this one was 2 more, and what happened in the areas? They were the same. So I suspect the 12 is the right one, but I need to check either the 11 or the 13 to make sure. So somebody said 13 first, so we're going to do 13. 13, 13, and what? 28, 2? So what's 13 times 22? And what do you think? Still not much, right? So what is my solution? What's the area, or what's the, let's see, it says, what are the lengths of the sides, if I've written it right? So I need 12 feet, 12 feet, and 24 feet. And all I did was get some check. But I kept track of what I was getting on check. Okay, working backwards. We talked about this a little bit last time as well. Working backwards is something, again, you guys have been doing the entire time you've been learning math. Because at some point, everybody doesn't know how to get some problem. You go to the back of the book and you wonder, how did they get that answer? You try to work your way backwards into it. And if it's a problem that's not in the back of the book, you try to find one similar, like that similar problem one, then you try and find your way backwards into it too. Same idea. So let's take a look at this one. And this one, you know, there are some problems that lend themselves to that very naturally. This is an example of that. All right, so one winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to be 32 degrees. What was the temperature at midnight? So, could we guess and check? That would be an option. We could do that. We could pick a number, and we could do the process that we went through right here to do that. That would be an option. But we can also go backwards, and that's what I'm showing on this one. Okay? So, we have several times that it tells us about. We talk about midnight. We talk about 5 a.m., that's the next time. And then we have 9 a.m. And then our situation concludes at noon, and we're told the temperature at noon. And what's the temperature at noon? 32 degrees. And it's probably very high at 32 degrees. But, all right, so we have a 32-degree temperature. But it told us that by noon it had risen 10 degrees to 32 degrees. So working backwards, what temperature would that make it at 9 a.m.? 22 degrees. Because from here to here it's supposed to rise 10 degrees. So we'll rise correctly. All right, so here's the 22 degrees. Now what happened between 5 and 9? Well, it said by 9 a.m. the temperature had doubled from what it was at 5 a.m. So it's 11 degrees at 5 a.m. because from here to here it's supposed to double. And then it says from midnight to 5 a.m. the temperature fell by 15 degrees. You add 20, they add 15, so it's 26 degrees. And it's supposed to fall here 15 degrees. So my solution after doing all of this was that it was 26 degrees at midnight. Does that make sense? So not all problems lend themselves well to any of these specific methods. That's why there's so many methods. If one method works for everything, well, that'd be just dandy. But it doesn't. Sometimes you're told, and sometimes you have choice. So like I said, this one works really nicely for working backwards, but you could have chosen something different, and it wouldn't be bad. I mean, you have options. Unless you're told specifically, you have options, and if you're told specifically, then you know. Yeah. I want to show you something that you're going to use in your group work. And have you guys done the 12 Days of Christmas before? Heard the 12 Days of Christmas on the first day of Christmas? What your love gave to me. We keep going from there. All right, so it asks you for the 12 Days of Christmas in one of your problems, your problem-solving ones. It's going to talk about which animal or creature, whatever you got the most of in your true love. So that's the question's going to ask you. I don't know about you, but I always get confused once we get down to about 9, 10, 11, which one comes next. I can see it backwards and wrong all the time. If I have a book at home and it doesn't have it in the right order, it's a children's book that is out of order. So I went online to find out which ones of them were in order so that you wouldn't have to look it up to find it out yourself. And I found this, and I thought that this was really interesting. And I don't know if you've seen this before or not, but there is religious connotation to the 12 Days of Christmas. This is the development of where these things came from. And I thought it was really neat. So the true love refers to God. The turtle doves are the Old and New Testament. French hens are faith, hope, and love, theological virtues. We have the calling birds for the 4 Gospels. The golden rings are the Pentateuch, which is the first 5 books of the Old Testament. The geese a laying is the 6 days of creation. Swans a swimming is the 7 gifts of the Holy Spirit. 8 maids a milking is the 8 beatitudes. 9 ladies dancing is the 9 fruits of the Holy Spirit. 10 lords a leading is the 10 commandments. 11 pipers piping is 11 faithful apostles. And then 12 drummers drumming is the 12 points of the doctrinal apostles' creed. So I thought that was really neat to have that. And so I put it in here because you're going to need to know how many of each of these there are when you get to that particular problem anyway. All right, so here's what we're going to do.